Today we're going to talk about autonomous differential equations. I put the definition here. A first-order differential equation is called autonomous if it is of the following form. A regular first-order differential equation can be written dy dt is a function of t and y. If that function of t and y doesn't depend at all on t, but just depends on y, in other words, just some function of y, we call this an autonomous differential equation. Let me write down a few examples that we've talked about recently. If we have dy dt is just a constant times y, this is an autonomous differential equation. One we looked at in the last video was dy dt is y to the 2/3. That's also an autonomous differential equation. Any autonomous differential equation, or not any, but almost any autonomous differential equation will have what we call equilibrium solutions. Anytime you have a root of this function capital F, in other words, a number c such that capital F of c equals 0, then you can have a constant function y equals c as a solution to this differential equation. One can just check immediately if y is a constant function, dy dt is 0, and if c, of course, is a root of capital F, the right side, f of c, is 0. So that constant function is a solution, and when the constant function is a solution, we call that an equilibrium solution. Why? Because if we think of y as modeling some phenomenon as a function of time t, if you have an initial condition, for example, where y is exactly equal to c, it will stay that way. Dy dt will always be 0, and that constant function y will tell you the solution forevermore. In our example, dy dt is a constant times y. We know that y equals 0 here is an equilibrium solution. And in fact, we've looked at this equation many times now. We know that the general solution is y equals a constant. I'll write that constant now as y naught e to the kt, where y naught is the initial value. That's just y at time t equals 0. So if you think of this as y is modeling the quantity of something, y naught is how much you have at time t equals 0, and at time t you'll have y naught e to the kt. It doesn't have to be a quantity because, of course, this y naught could be negative. And if I plot these solutions, here's the t-axis, here's the y-axis. Of course, there's the equilibrium solution, the y equals 0 solution. If you have any initial value that's in the upper half plane, in other words, y of t naught equals some positive number, let's say you start here, you can see that you'll have some sort of solution that goes up exponentially like that. And you'll get a family of solutions that look like this. If you start with the negative number, it'll look like this. So that you can see the whole family of solutions there very easily. When you have an autonomous differential equation, the slope field or direction field is very simple. Notice that for a particular value of t is along this horizontal axis, and of course y is here along the vertical axis. For a particular value of t, you'll have these different slopes depending on what y is. But then if you change the value of t, you'll have a column here that looks identical because our function here, differential equation dy dt is just some function f of y. It doesn't depend on t. Now, this is the slope field for the differential equation dy dt is y squared times 1 minus y. That's the one that I've shown up here. And immediately you can see that you have equilibrium solutions y equals 0, and y equals 1. Those are clearly the two roots of this function, y squared times 1 minus y. And if I draw those solutions in here, I'll draw them here. There's the green one here. And the red one here, y equals 1. Those are our equilibrium solutions. And now here it's not really too clear what's going on in between, so let me try to elaborate a bit. We can draw what we call the phase line. Get back to black. This is just different values of y, so I'm putting it on a vertical axis just so it matches the vertical axis here for the y-axis. And I'll mark the two special points. Here's 0, and here's 1. These are the roots of y squared times 1 minus y. So that this function f of y is 0 at 0 and 0 at 1. These are the only roots, so everywhere else it's either positive or negative. And since this is a continuous function and we've marked all the roots, in each region here between 0 and 1 or above 1 or below 0, there's the same sign for all the values of f of y. We just have to figure out what it is. So let's start with the middle interval here. If y is between 0 and 1, what is the sign of this function? This is our function that we've been calling capital F of y. If y is between 0 and 1, that's positive and that's positive, so capital F of y is positive. If y is bigger than 1, that's negative and that's positive, so it's negative. What if y is less than 0? If y is less than 0, that's still positive, and that's positive, so it's positive. So we have positive, positive, and negative, and you can see that from the slope field, that here you have positive slopes. In between here, it's not so obvious from the bad picture that I have here, but you see there are actually positive slopes there, and for y bigger than 1, you have negative slopes. That tells you right away that if you give me an initial condition that starts somewhere in this middle region, where an initial condition, say y of -2 is, I don't know, a half, right there, and you ask what the solution looks like, you know it's going to be increasing, but increasing slower and slower and slower, and be asymptotic here to the y equals 1 solution. If we move this to the left, we'll see it'll be decreasing and asymptotic to the lower solution. And we'll get a whole, depending on the initial condition, we'll get a whole family of curves that all look something like this, all asymptotic to y equals 1 to the right, and to y equals 0 on the left. But if you give me any initial condition down with y below 0, you'll get a solution curve that looks like this, asymptotic to y equals 0. If we start here, kind of like this. And similarly, if you give me any initial condition up here with y bigger than 1, it will decrease and be asymptotic to y equals 1 from above. We can classify the equilibrium solutions in the following way. Look at this equilibrium solution y equals 1. Imagine, here again, you're measuring the quantity of something, and you deviate from that equilibrium solution just by a little bit, say a little bit bigger. Well, the solution you'll get will move back towards the equilibrium solution. If you deviate by having a little bit less than 1, again, your solution will move back towards y equal 1. So we call y equals 1 is a stable equilibrium. Let's look at y equals 0. Imagine we're on this equilibrium solution y equals 0, but we deviate somehow through some randomness, deviate just a little bit off of y equals 0. Well, a small deviation above y equals 0, if we then follow time as it progresses, will lead to a solution that moves up towards y equal 1. It will move away from our y equals 0 equilibrium and towards some other equilibrium. But if we deviate a little bit below y equals 0, our solution will move back towards the equilibrium y equals 0. So we call y equals 0 a semi-stable equilibrium. Semi-stable because it's stable from below, but unstable above, meaning if there's a small deviation above, it will move away. There's a third type of equilibrium, which we'll see in the next example, and that would be an equilibrium where a deviation in either direction has solutions that move away from that equilibrium solution. So let's look at the next example. We have dy dt here equals 2 minus y times 1 minus y times 2 plus y. I've already left the factors because then it's very easy to see what the phase line looks like. This has roots y equals 2, y equals 1, and y equals negative 2. So our equilibrium solutions are exactly y equals 2, y equals 1, and y equals negative 2. And if I plot those here, here's negative 2, here's 1, and here's 2. We can look at the sign here of this function f of y. This is the y-axis, and this is the phase line. If y is bigger than 2, then this is negative, and this is positive. So we have positive slopes, and you can see that in the slope field, the direction field for this differential equation. If y is between 1 and 2, then this is positive, this is negative, and this is positive. So the product will be negative. And you can see very easily we have positive here and negative here. So let me draw the equilibrium solutions here using blue, red, and green. Here y equals negative 2 will be an equilibrium. Oops. And using green here, we have y equals 1. That's in here. So the slope field didn't show the points right in between, but there's an equilibrium solution right here at y equals 1. And then up here above, you can see the equilibrium solution, y equals 2. So what can we say about characterizing these equilibrium solutions? Well, if there's a small deviation away from the equilibrium solution y equals negative 2, you can see that solutions will diverge very quickly here. Erase that. Should be even steeper, very steeply diverge right away. So you get asymptotic very quickly and then diverge very quickly downwards. Or if there's a deviation here, they'll go way up very quickly and go towards the equilibrium solution y equals 1. So y equals negative 2 is what we call an unstable equilibrium. Y equals 1 is a stable equilibrium because, as we've already seen, if you start out a little bit below y equals 1, the solutions will move back towards y equals 1. If you start out a little bit above y equals 1, the solutions will go down towards y equals 1. So y equals 1 is a stable equilibrium. And I'll leave it to you to look at this and see that. And again, you can tell from the phase line as well, y equals 2 is an unstable equilibrium.